This video mainly focuses about the key design choices we made for our sequence game, presented by Team 80. First, here is a brief introduction to our project. We used the Q-learning approximation algorithm, which is a type of reinforcement learning. Basically, this algorithm represents the Q value as a linear combination of features and weights, and it helps to reduce the massive state space we would normally have with the standard algorithm. The content of this video will be divided into three parts. First, we'll talk about the strategies we developed for the special rules in sequence game. The first special rules is 2 ijacks and 1 ijacks. For these two special cards, we mainly define the features during the card drafting phase. We set 2 ijacks as feature 0 and 1 ijack as feature 1. If our agent draws one of these cards, the value for that feature will set to 1. As you can see in the GIF below, our agent prioritizes drafting jacks when they appear in the draft cards. Next is the second special rule, central occupation. For this rule, we define three features to guide our strategy. This strategy prioritizes the drafting of cards that help occupy the center, and placing chips in the center whenever possible, and finally removing opponent's chips from the center. When any of these actions happen, the corresponding feature is set to 1. In the GIF below, you can see the blue player removing the red player's chip from a center spot, and then taking it over to win. The third special rule is corner utilization. For this rule, we don't define a direct feature. Instead, if a corner's color is converted to our agent's color, we then use our general strategy, the one that assesses the potential to form a sequence, to make a combined judgment.
Our agent decision-making is based on two general rules, sequence detection and sequence potential detection. Sequence detection means that after each simulated move, we check if a new valid sequence is formed. Sequence potential detection evaluates how likely a move can lead to a future sequence, which means the higher the density, the better the potential. Based on the general rule, we designed two strategies, aggressive and defensive. Our aggressive strategy focuses on maximizing our own advantage. It includes two types of action, place to win and remove to win. For example, in this case, our agent play a 10 and draft an S, and on the next move playing the S almost complete two sequences at once. And the defensive strategy aims to counter the opponent's threats. It also includes two types of action, place to block and remove to defend. For example, if the opponent already have a 4 in row, and our agent will choose an S from the draft to block it. On the next turn, it played S to break the threat.
Process. Our engine learns to play sequence through temporary differences learning, adjusting its strategy based on the gap between what it expects to happen and what actually occurs. During the gameplay, it sometimes tries new moves to discover better strategies and constantly fine-tuning its approach through experiments. Compute action Q value is one of the most important actions in our engine. This function solves the fundamental challenge in sequence. The game has far too much possible ball state to evaluate individually. So our solution is using linear function approximation. It allows us to generalize across similar situations. This function works by extracting 14 features that represent critical aspects of the game state and potential action. These features are then combined with the weight through the first formula. During the training, the engine calculates the weight through experiments. After each move, we update the weights using the second formula, where alpha is the learning rate. We use 0.1 in our project, and delta is the temporary differences error. It calculates by reward plus the maximum Q value of the next day minus the Q value of the current day. And SA is the future value. We think this equation is really powerful because first, if we have a positive delta, it will increase the weight of the features that lead to good outcomes. If it's negative delta, it decreases the weight for features that lead to disappointment. And if it's high feature value, it makes large adjustment to the features that will strongly present. If it's zero feature value, it will no change. Finally, we're looking at the weight of an engine learned, and we can find something interesting. The higher value, around 99, appear for 2 ijack and the sequence information. The median range value appear for draft card sequence potential and the boarding sequence. It gives us the clear insight into how our engine makes decisions. The higher weights largely increase the possibilities that action with those features will be selected. When these features are present, they dominate the Q value calculation, making the engine strongly prefer this action.